Welcome everyone to our lesson. In this lesson, we're going to talk about the concept of sampling distributions and the central limit theorem, and then it's also abbreviated CLT. You can see that here. Now, sampling distributions are fundamental. They're very important in statistics because they're going to help us when we get to the second half of the class and we talk about inferential statistics. It's going to be key to that. And this helps us understand how sample means behave when we repeatedly take samples from a population. And the central limit theorem is a powerful theorem that tells us under certain conditions, the distribution of the sample means will be approximately normal, even if the population itself is not. Now, I know that's a lot to take in at once, which is why I created this diagram here. I'm going to walk you through this diagram to help you visualize what a sampling distribution is. So, on the left, you see a diagram representing a single sample from a population. This circle represents one sample, and those little black dots, imagine that those are the pieces of information, the data that was collected in the sample. And then when you collect the information, you calculate the average, and that's your X bar, the sample mean. This is what's called the population distribution. Now on the right, we see multiple samples. So here's one sample, here's a second sample. You can see that we have 6 of them. I can only fit 6 on the page, but imagine we take many, many, many samples, and each of those samples has data collected, and then you take the average for each sample. So now we have a collection of all these means from all the samples. When we graph all those means, that's when we get the sampling distribution. The sampling distribution is the graph of all the means, and the population distribution is the graph of all the individual data values collected from one sample. So hopefully this helps you visualize what I'm talking about when I say I'm taking many, many samples, I'm finding the means of all those samples, and then I'm using all those means to graph the sampling distribution. Now, below here on the left, we see a whole bunch of different sampling distributions. These are just the typical ones. It doesn't mean that there aren't any more. I just graphed some of the basic ones. We have the normal distribution. That's here. We have right skewed. We have uniform. We have bimodal. We could have left skewed as well. No matter what the shape of the population distribution has, the central limit theorem tells us that the distribution of the sample means will tend to look normal as the sample sizes increase. So if you look over here, when I graph all the averages, the sampling distribution should look like a normal curve as that sample size gets bigger and bigger and bigger. Now, some notation, when we're looking at the population distribution, when we're graphing the individual data values of one sample, we've already talked about this, but let's review it. Here are the symbols for the population distribution. We have mu for the mean, and then we have sigma for the standard deviation. When we're looking at the sampling distribution, we have different symbols. So we're going to use mu with a sub X bar, like a subscript, and then we're going to use sigma with a subscript of X bar. Now, the mean of the sampling distribution and the mean of the population distribution should be the same. However, the standard deviation is going to change. The standard deviation of the sampling distribution is going to be whatever the standard deviation of the population distribution is, and then you divide that by the square root of the sample size. That's how you calculate the standard deviation of the sampling distribution. All right, so let's look at the central limit theorem so we know what requirements we need in order to use this. For sufficiently large sample sizes, the distribution of the sample means approximates a normal distribution regardless of the underlying population distribution. So again, I'm going to stress this over and over again. You're probably going to get sick of hearing me say this, but it's important that it sinks in. We have the population distribution, which is the underlying distribution, and that's the distribution that graphs the individual values from one sample. When we're looking at the distribution of the sample means, that's when we take many, many, many samples, we calculate the average of all of those samples, and the averages are what we're graphing. And that, under certain conditions, will always have a normal distribution. It has to meet these requirements that we're about to talk about. And here's the notation here that we just mentioned. So because this is going to be normal, we're going to use the N notation. Because our variables are means, we're going to have X bar with our tilde, then we have the capital N, and then our mean and standard deviation is the mean and standard deviation for the sampling distribution. So we're going to make sure that we label that with our sub X bar. So here are the requirements needed to use the central limit theorem. The data must be sampled randomly. The samples are independent. The sample size for each sample has to remain the same. In other words, I cannot take a sample of 5 and then a sample of 10 and then a sample of 20 and find all of those averages and use the central limit theorem that way. All of the sample sizes need to be the same. Now, this last condition is an OR statement. Only one of these conditions need to be met to satisfy the OR statement. So in order for this fourth requirement to be met, the sample size needs to be greater than or equal to 30, or the underlying population is normal. So it only needs to satisfy one of those. So for the first few examples, we're going to walk through some scenarios and we're going to look through some statements to decide if they're true or false to help us understand the difference between the population standard deviation and the sampling distribution and when we can use the central limit theorem. All right, let's take a look at example 1. Example 1 states that a local bakery tracks the number of croissants sold per day. The daily sales follows a heavily skewed right distribution with an average of 23 croissants per day and a standard deviation of 8 croissants. So I want to point out that this says, this is important, I'm going to underline it here. Let's see. The daily sales follows a heavily skewed right distribution. So when we're looking at those individual values for the population, if we look at that graph, it's going to be skewed right, not normal. Then it goes on to say the manager randomly selects 12 days and records the average number of croissants sold per day. So the first thing we should do is talk about if using this scenario, if we can use the central limit theorem here. Does the central limit theorem apply? And in order for us to be able to use the central limit theorem, we need to have randomly selected samples and observations to make sure that we have independence of observations. And then the other thing is it needs to meet one of the true criteria. It only needs to meet one. It could be both, but it only needs to meet one of these. So the population distribution is normal, or the sample size is big enough, and we call big enough 30 or more. Okay, so looking at this scenario, the samples are randomly selected, so we know that there's independence. And then the other thing we need to check is about the population. Is the population distribution normal? And that's why I underlined it in the second sentence. It is not normal. It is skewed right. So it doesn't meet that criteria, which means in order to use the central limit theorem, it needs to meet that second criteria, which it needs to have a large enough sample size. And in this case, our sample size is 12, which is not big enough. We need 30 or more. So it doesn't meet one of those two criteria where we could say that the central limit theorem applies here. So in this scenario, we would not be able to use the central limit theorem, which means when it comes to finding probability, we would not be able to use the normal distribution. All right, so let's look at the first statement. We're going to look at each of these statements and decide if they are true or false. The first statement says, the sample mean distribution, meaning the sampling distribution, is normal because the population is normal. That would be untrue. The population distribution is clearly labeled as skewed right. Okay, let's look at the second statement. The second statement says, I can use the central limit theorem because the sample size is adequate for any distribution. Again, this is false because we have heavy skewness, so we need a large sample, and that means we need 30 or more, and in this case, we don't have that. So I'm going to mark this as false. All right, the next statement says the probability that the average exceeds 25 can be found using the normal distribution. Now, because we cannot use a central limit theorem here, we cannot use normal probability to find the probability when we're talking about averages here. So this is also going to be false. All right, the next statement says, I cannot use the central limit theorem because the sample size is too small and the population is skewed. This is definitely correct. This is what we discussed on the reasons why we cannot use the central limit theorem. Okay, the next statement says the standard deviation of the sampling distribution is 2.31. At the beginning, when we were reading through the scenario, we identified that the sample size is 12. The standard deviation for the population is 8. The mean was given as 23. So even though the central limit theorem doesn't apply here, I want to still practice finding the standard deviation for the sampling distribution with you. And so in order to do that, remember the formula is you take the standard deviation of the population, which is 8, and you divide by the square root of the sample size. In this case, the square root of 12. And when you put that in on your calculator, you're going to get approximately 2.31. So this would be a true statement. All right, last statement. If the sample size was 30 or larger, we would use the normal distribution despite the skewed population. That would be true. Because this is skewed right, in order to use the central limit theorem, we would have to be able to meet the other condition, which would be that the sample size needs to be 30 or bigger. And that's what this is saying. If the sample size was 30 or bigger, we could use the normal distribution. This is saying then the central limit theorem would be applied, and this is true. All right, looking at example 2, it says a ride-sharing company analyzes trip durations in Boston. The trip time follows a heavily skewed left distribution with an average of 18 minutes and a standard deviation of 12 minutes. The company randomly selects 64 trips and calculates the average trip duration. We're going to decide whether or not the central limit theorem applies here, and then we're going to make sure that we indicate whether these statements are true or false. So it says here that the company randomly selects the 64 trips. So that way we know that because they're randomly selected, we know that they're independent. They're different riders from different trips. Now, can we use the central limit theorem here? Again, it tells us that the population is skewed, so it doesn't meet that first criteria, but it does say that we have a sample size larger than 30. So we can use the central limit theorem here, which means when we try to find probability involving averages, we can use the normal distribution. Now, if we're trying to find the probability of individual values, that refers to the population distribution, and that is skewed left. So we cannot use the normal distribution when we're looking at probability for individual values. But for averages, when we're finding probability of averages, we can use the normal distribution. So let's take a look at our statements here. The first statement says the sample mean distribution is normal because the population is normal. This is false. The sampling distribution isn't normal because the population is normal. The population, we're told, is skewed left. The sampling distribution is normal because the sample size is 30 or bigger. That's why. So this statement is false. Okay, let's look at the second statement. I can use the central limit theorem here because the sample size is large enough even though the population is skewed. That would be true. So even though the population is skewed, it meets the criteria of the population being 30 or bigger. So that works. Okay, let's look at the next statement. The probability that the average trip, so we're talking about probability of averages. The probability that the average trip time over 64 trips is less than 16 minutes can be found using the normal distribution. This would be true. Because we're talking about probability involving averages, the central limit theorem tells us that we can use the normal distribution here because the central limit theorem applies. Okay, the next statement says, I cannot use the central limit theorem because the population distribution is skewed. That is false. The next statement says the standard deviation for the sampling distribution is 1.5. Let's check. So we identified in the scenario that the sample size is 64. The population standard deviation is 12. The mean is 18. So in order to find the standard deviation for the averages for the sampling distribution, we take the population standard deviation, which is 12, and we divide it by the square root of the sample size. So we're going to take 12 divided by the square root of 64, which is 12 divided by 8, and that gives us 1.5. So this is a true statement. Okay, last statement. The sample size of 64 is sufficient to overcome the skewness of the original distribution. This is correct. The sample size needs to be 30 or larger, and it is, so this is true. All right, looking at example 3, we have a fitness tracker company studies daily step counts of users. The daily steps follow a normal distribution with an average of 8,500 steps and a standard deviation of 2,200 steps. A researcher selects the same 40 individuals and tracks their steps for consecutive days, calculating weekly averages. So first, let's take a look at if we can use the central limit theorem here. Now, at first glance, we see that the population distribution is normal. We have that right here. We also have that the sample size is 40. So right now, those two criteria are met. This can be a little bit misleading because remember, even though we put a lot of focus on these two conditions, there's still that other condition that the samples need to be independent. Those observations need to be randomly selected and independent. And in this case, notice that the researcher keeps selecting the same 40 for each of his samples. So these are not independent. So if they were independent, then we could use the central limit theorem here because the other two conditions are both met. But because independence fails here, we cannot use the central limit theorem. All right, so let's go through and check the statements and decide which ones are true and which ones are false. Okay, the first statement says, the sample mean distribution is normal because the population is normal. So this isn't always going to be true. It might be true, but it's not a guarantee because of the independence issue. So we're going to mark that as false. The second statement says, I can use the central limit theorem because the sample size is adequate. The sample size is adequate, but we still can't use the central limit theorem here because it doesn't meet that independent condition. So this is also going to be false. So the third statement says the probability calculations are valid because we have enough observations. Again, that would be false, and it's false because of the issue with independence. Okay, the next statement says, I cannot use the central limit theorem because samples are not independent. It's the same people tracked over a period of time. That is correct. We've identified that that is an issue here. Okay, the next statement says the standard deviation of the sampling distribution would be 348 if independence was satisfied. So practicing finding the standard deviation for the sampling distribution, remember we take the population standard deviation, which in this case is 2,200, and then we would divide that by the square root of the sample size, which would be square root of 40. When we do that, we get approximately 347.85. And rounding it to the nearest whole number, we would get approximately 348. So if we were not concerned about independence here, this would be our standard deviation for the sampling distribution. Okay, last statement. Independence is violated due to the repeated measures design. So this is a fancy way of just saying that independence fails here because the researcher picked the same 40 people each time he did this trial. So they're not completely separate samples. So this would be a true statement. Example 4 says a luxury hotel monitors guest satisfaction scores, which are normally distributed. So here, right here, we're going to quickly pause to underline that. The population distribution is normally distributed. So that's important. We're told that we have a mean of 4.3 out of 5 and a standard deviation of 0.6. The manager randomly selects 18 guest reviews and calculates the average satisfaction score. So he's randomly selecting these 18 guest reviews. So independence here is good. So that's met. And so let's take a look at whether or not the central limit theorem applies here. So because we're told that the population standard deviation is normal, then automatically we know that the sampling distribution is going to be normal for any sample size because the population is going to be normal. So when the population is normal, regardless of sample size, as long as obviously the independence holds true, the sampling distribution is going to be normal as well. So the central limit theorem here automatically gets applied. Okay, so now let's look at these statements. The first one says the sample mean distribution is normal because the population normal. That is true. Second statement, I can use the normal distribution for the sampling mean because the underlying population is normal regardless of the sample size. This is also correct. When we are finding probabilities for averages, we can use the normal distribution because we know that the sampling distribution is additionally normal because the population is normal. Okay, the probability that the average satisfaction over 18 reviews exceeds 4.5 can be found using the normal distribution. This is correct. When we're finding probability involving averages, we can use the normal distribution because the central limit theorem applies here. Next statement says, I cannot use the central limit theorem because the sample size is less than 30. So even though the sample size is less than 30, in this case it's 18, we can still use the central limit theorem because the population distribution is normal. So this is false. We can use the central limit theorem. Next statement, the standard deviation of the sampling distribution is 0.14. All right, so let's check. We've identified that our sample size is 18. Our population standard deviation is 0.6. The mean is 4.3. So to find the standard deviation for the sampling distribution for the averages, we're going to take the population standard deviation, 0.6, and we're going to divide by the square root of the sample size, so the square root of 18. And when we divide that on our calculator, we're going to get approximately 0.14 when we round to two places. So this is correct. Last statement, it says when the population is normal, any sample size allows the use of normal distribution for the sampling means. This is true, although you might want to put a little note in there. This is assuming that the independence condition is met as well. So as long as the independence condition is met as well, yes, this would be true.